Hello friends, welcome back to my channel. I'm Mr. Chutke helping you with chemical properties of haloalkanes. We are in part 4 of haloalkanes. In part 3, we have just begun with the chemical properties of haloalkanes in part 3, and there we have just seen one reaction wherein we have converted uh, haloalkane to alcohol, obviously by using aqueous KOH. I've also shown what is the effect of alcoholic KOH. If you have not seen part 3, I'll drop the video link in the description box. Please have a look at part 3 before you continue with part 4. In that part 3, we have also covered SN1 and SN2 mechanism in ultra detail, okay, which is very important for your board exam. Now, let us see the remaining reactions left in chemical properties of haloalkanes. When I say chemical properties of haloalkane, it is but obvious that we are going to take haloalkane on the left hand side and see what are the different things you can prepare using haloalkane. So, haloalkane is a functional group which can be converted into cyanide. It can also be converted into isocyanide. It can also be converted into amines. It can also be converted into an ester. It can also be converted into an ether and also into a nitroalkane. I've not covered alcohol over here because that we have already done in part 3. So we are going to see how we can prepare haloalkane to all these different kinds of functional groups. So let us do them one by one. RX to RCN. A standard haloalkane like CH3CH2Br, that is bromoethane, and let us convert this bromoethane into its corresponding cyanide. Let's see how we can do that. So we are going to take KCN over here, potassium cyanide. Potassium cyanide, obviously you must have guessed it by now that potassium cyanide is an inorganic compound, so it will ionize, it will dissociate. K plus and Br minus will combine to form KBr, and cyanide will get attached over here. It's obviously a negative replaced by negative. A negative Br group is replaced by a negative Cn group, cyanide group. Okay, obviously it's a negative replaced by a negative reaction, and needless to say that it is nucleophilic substitution. And because this is a primary haloalkane, it will follow SN2 mechanism, which we've discussed in the previous part. So CH3 CH2Br, instead of Br, who's going to come over here? Cn will come over here, cyanide will come over here. Now there is a trick in naming this compound. If you are going for common names, you simply split it from here. This is ethyl, this is cyanide, ethyl cyanide, as simple as that. But if you are going for IUPAC, then you need to consider all the 3 carbons which are visible over here. 1, 2, 3, all the 3 carbons. And when we are having 3 carbons, obviously we have the prefix as propan, okay, and we remove the E from propane and use propan nitrile. Nitrile will be the suffix because we are having this triple bond N. This triple bond N will indicate that it is a cyanide. It's a nitrile, triple bond N. So propan nitrile will be the IUPAC name of this compound. Okay, now after we have got propan nitrile, now moving towards the formation of isocyanide. Now you need to note something interesting happening over here, that when we use KCN, now KCN is a strong electrolyte, it dissociates quickly into K plus and Cn minus. But what about AgCN? AgCN is a little lethargic to dissociate. It's a weak electrolyte, so it does not dissociate immediately. So what happens? So because it does not immediately form Ag plus and Cn minus, now because it does not dissociate easily, nitrogen gets bored, it gets bugged. So it says that I'll start donating electrons from the nitrogen end. Okay, then because it is donating electrons from the nitrogen end, what happens is it gets attached from the nitrogen side and then carbon follows. Later on, Ag, because of the slow dissociation, will combine with Br, forming AgBr. Just to mention that AgBr will give you a yellow colored PPT. Like AgCl is white in color, AgBr is yellow in color. So this is particularly ethyl isocyanide as far as the common name is concerned. Whereas for IUPAC, needless to say, it will be propan isonitrile. Okay, propan isonitrile. Earlier it was propan nitrile, that's what we had formed. Here we are going to get propan isonitrile because in place of KCN, we have used AgCN. You need to remember this, okay? Because if you use KCN, you get cyanide product. And if you use AgCN, you are bound to get isocyanide. okay, because of the slow dissociation. Fine. Now after isocyanide, let's go for converting haloalkane into an ether. Okay, this CH3CH2Br, let us convert this into an ether. You must have seen this reaction in ethers, that is nothing but Williamson's synthesis. Now I'm purposefully writing a few letters capital over here. That is our mnemonic that's going to help you remember the reaction. Okay, that's going to help you remember the reaction. Have a look over here. So A is going to remind you of alkyl halide, which we are using. Of course, alkyl halide is also called as haloalkane. And SO or S will remind us of sodium alkoxide, which we are going to use. Okay, so sodium alkoxide is basically formed by a reaction of sodium with alcohol. So sodium when reacts with alcohol, it will form sodium alkoxide. Here I'll take sodium ethoxide, CH3CH2ONA. Sodium ethyl oxide, sodium ethoxide. Okay, sodium ethoxide, and this is bromoethane. Sodium ethoxide and bromoethane. Okay, so here what are we going to get? E stands for ether. Okay, E stands for ether is what is going to be prepared. Na and Br will obviously combine with each other to form NaBr, and जहां से तोड़ा है वहीं से जोड़ना है, and that's how we will be getting, we'll be combining whatever is left. But नकल करने में अकल चाहिए, नहीं तो शक्ल बिगड़ जाती. Just don't blindly copy paste. Some children may write CH3 CH2 CH3 CH2. Don't do that. Okay, जहां से तोड़ा है वहीं से जोड़ना है. CH3 CH2, and then we have this O, and then it's connected to CH2 CH3. So यहां से कॉपी करके यहां पे पेस्ट करो. नकल करने में अकल चाहिए, नहीं तो शक्ल बिगड़ जाएगी, इसकी प्रोडक्ट की शक्ल बिगड़ जाएगी. देन हियर वी आर गेटिंग व्हाट? इथॉक्सी. दिस इज एन ईथर. इथॉक्सी ईथेन. ROR is ether. Ethoxy ethane is the ether which we have prepared. Okay, so now in this particular reaction you need to remember that whenever you are performing this Williamson synthesis, make sure that you are not using a tertiary haloalkane over here, because in case if you use a tertiary haloalkane, remember that tertiary haloalkanes prefer elimination over substitution. That means Br is not going to get replaced, and this OCH to CH3 is not going to get attached. It's not going to be a replacement or a substitution reaction. Rather, it's going to be an elimination reaction. Sir, मतलब क्या? मतलब ये कि haloalkane को ether में नहीं convert कर पाओगे, replacement नहीं हो पाएगा, substitution नहीं हो पाएगा, elimination हो जाएगा, जिसके चलते आपको alkene मिलेगा. ठीक है, चलो करके दिखाते हैं आपको. Like what I am saying is you are not allowed to use tertiary haloalkane in विलियमसन सिंथेसिस, क्योंकि अगर आप टर्शियरी हैलोअल्केन यूज करते हो विलियमसन सिंथेसिस में तो वो आपको ईथर देगा ही नहीं, रादर क्या दे देगा? It will give you an alkene. So check Na and Br, this will combine with each other to form NaBr, no doubt about that. Then because this is a tertiary haloalkene ना, तो CH3O और यहाँ से एक H निकल आ जाएगा, तो CH3OH बनेगा, and then we are left, CH3OH तो बन गया, ये भी चला गया, इधर से हाइड्रोजन चला गया, we left with this compound. So that is going to give us an alkene, CH3, copy paste, CH3CCH3. Now this is CH2. Okay, this नीचे वाला part CH2, because one hydrogen is gone. So in order to balance the valency, I'll put a double bond which will make this as isobutylene, common name, and IUPAC name will be 2-methyl propanene, 2-methyl propanene, or an alkene. So did you get an ether? Yeah, using Williamson synthesis, you were supposed to get an ether, but what you did, instead of me refusing you or asking you not to use an tertiary haloalkane, still if you zid se aap tertiary haloalkane use karoge, then what is going to happen? You're not going to get an ether, rather you'll get an alkene, because tertiary haloalkanes, I repeat, tertiary haloalkanes do not prefer undergoing a substitution reaction. They rather prefer undergoing an elimination reaction. They prefer elimination over substitution. So that was Williamson synthesis. That was converting haloalkane to ethers. Now we are moving towards converting a haloalkane. I'll again take a standard haloalkane, bromoethane, and react it with NaNO2 and NaBr will combine with each other, of course, Na and Br, and NO2 will get attached over here. So simple reaction, we get a nitroalkane. Which nitroalkane is this? This is nitroethane, isn't it? Nitroethane. Okay, now come on. One more reaction, that is ammonolysis. Yeah, what is the word? What is the meaning of the word ammonolysis? You should be able to guess it by now. That, see, what is electrolysis? Have you studied about electrolysis? It's breaking down of a chemical bond using electricity. What is photolysis? Breaking down of chemical bond using light. What is hydrolysis? Breaking down of chemical bond using water. Similarly, what is ammonolysis? Breaking down of chemical bond using ammonia. And one more, ozonolysis, breaking down of chemical bond using ozone, will be ozonolysis. Okay, so in ammonolysis, obviously we are going to use ammonia with haloalkane. Okay, and can I write, with your permission, can I write ammonia like this, NH2 and H? So H and Br will combine to form HBr, and NH2 will get attached in place of Br, which will give you CH3 CH2 Br, sorry, CH3 CH2 NH2, which is nothing but, uh, you can call it as ethanamine. Ethan, E nikal ke, we'll substitute E with amine, replace E with an amine, ethanamine. Okay, so this is formation of amines. Now, anything else left? Yeah, formation of ester is remaining. So we have to convert haloalkane to ester, CH3 CH2 Br. This time I'll take silver acetate, CH3 C double bond O OAG. This is your silver, this is your acetate, silver acetate. And you must have guessed it by now that Ag will combine with Br to form AgBr, and the remaining things will get connected automatically to form CH3. I'll copy paste from here, CH3 C double bond O. After this O, जहां से तोड़ा है वहीं से जोड़ना है, CH2 CH3. So this is the alkyl part of an ester, and this is the alkanoate part of an ester. So alkyl alkanoate is the IUPAC name for esters. So this is ethyl ethanoate as the IUPAC name for esters. Okay. So I've covered the major reactions in chemical properties of haloalkanes. Have a look at your textbook, and please write in the comment box if any reaction is remaining in the chemical properties of haloalkanes. Thank you.